Okay, I'm going to show you one more example where time dependence plays a big role. Okay, so in this example, we're going to take a can of honey. Okay, nice can of Utah honey, just famous for its honey. And we have a little plate that, maybe for tasting, we dip in the honey and then we take out the plate. So obviously the honey is gonna form kind of like a thick film that looks like this, and then it's gonna start drizzling. And our goal is to find the rate of change of the width at the bottom, this width b of t at the bottom of the plate. So we're going to model this as, we're going to idealize it as a plate of length L, height L, and we're going to assume the honey layer is this nice triangle, okay? And this is the width b of t. Okay? We are also given the velocity right here at the bottom of the plate. So again, we're going to draw this triangle of height L, width b, and the velocity over here is given by this velocity profile. U is equal to some value u times y over b of t, and this would be our y-axis. Okay. The value of this guy is some constant. Let's say it's about 10 to the minus. It's about 10 to the minus 3 meter per second. Okay. All right. So we simply take this as our control volume. Okay. This as our control volume. Now, strictly speaking, this control volume is deforming, but we're going to neglect the deformation rate, and we're just going to strictly be approximating this change in the width b. Okay, so we're going to write the law integral d by dt of rho dv, rho of honey, over our control volume, plus the integral of rho u dot n ds over the control surface, that's equal to 0. Now this guy, d by dt of integral of rho dv, is simply d by dt of rho times the volume, because rho is constant, and the volume is simply given by base times the height. We're going to assume unit depth for simplicity, or whatever other depth you're interested in. Just assume unit for simplicity. So d by dt of rho times b of t times L. Okay, so that's our volume. So that gives us this rate of change, which would be rho L dB by dt. Next is the outflow. So we only have outflow in this case. We're going to only deal with the outflow in this case, and that's the integral over the control surface of rho u dot n ds, and that's simply equal to the integral of rho, that's uy over b of t times dy, integral from 0 to b of t. Again, we've assumed unit depth, and that gives us rho u over b, y squared over 2 between 0 and b of t. That gives us, is going to give us b squared, so you get rho u over 2b of t. Finally, putting things together, we get rho L dB by dt plus rho u over 2b of t is equal to 0. That gives you the ODE. We can simplify the rows over here, and that gives you the ODE for the change in the width. Okay, in the width as time goes on, and you can easily solve this. This is going to provide an exponential solution. So this is strictly an ODE, so we can change the partial into a total derivative. That's dB by dt is equal to minus u over 2L b of t, and the solution b of t is some b0 e to the minus u over 2L t. You can verify this, that dB by dt is b0 times minus u over 2L b of t, and so things cancel out very nicely. Okay, and that is our solution over here.